Okay, this is the answer key to the last of the worksheets from that last packet. And I want you to go ahead and look this over. Pause if you need to so that you can make sure you have the answers correct, because the goal of this short, hopefully short, video is just to go over the patterns with you and make sure that you're picking up the big idea that we're going to carry on into the next thing. So the first thing I want you to notice is that we want to be reminded that as long as we're talking about an atom, then we know that the number of protons and the number of electrons are going to be the same. Of course, the protons are positive, you know the electrons are negative, atoms are neutral, ions are not neutral. So the number of protons is always equal to the number of electrons in an atom. Here with the electron distribution, the idea was that you just looked at the end. You're just looking at the end. So when we learned how to look at the periodic table and point to the element's location on the periodic table and identify that location as part of the S portion of the periodic table or part of the P portion, and then by that specific location we knew exactly where that last electron would be in that electron configuration. And so that's what we're talking about here for that column. And then hopefully you're seeing that what we really have here on this chart is the filling of that second energy level, beginning with lithium, 2s1, 2s2, etc. When you look at your periodic table, we're moving in that second row, which we call a period. The periodic table is periodic, and so we have the second energy level coinciding with our second row, and so we're just filling that one by one. Neon has 8 valence electrons. Lithium has 1. Again, we're really talking about valence electrons here. And when we learn to count valence electrons, there's our lithium with 1 valence electron. Beryllium has 2 valence electrons. Boron has 3 valence electrons. Carbon has 4. Nitrogen, of course, with 5. Oxygen with 6. Fluorine with 7. And then neon, which has an octet, 8 valence electrons. And we know that because we're looking at what column that element is in. And when we look at periodic tables, we can see that we have these labels on many periodic tables which talk about which group or family an element is in. And what's nice about the way they're numbered is that the last number in the family number is the same as the number of valence electrons. So when we look at the family number 14, it has 4 valence electrons. Where is this number, this going 1 to 2, now I'm jumping to 13, 14, and 15. What's going on with those numbers? If that looks confusing to you, look back at your periodic table and be reminded that after the S section of the periodic table, now we have that D section kind of shoved in there in the middle, right? And that D section has exactly 10 elements, which is room for 10 electrons. So that's where you're getting this jump from number 2 to number 13. And you're adding in those columns for that D section. So if we numbered all the columns from left to right, we're going to get 1 and 2. Then we're going to have numbers 3 through 12, which is our D section of the periodic table, and then 13, 14, 15, up to 18. And again, the idea is that you'll see that that pattern, even if we just look at that family or group number, the last number there is a shortcut to our number of valence electrons. So the periodic table is pretty amazing, the way that it's laid out. Once we understand that that information is there, it's at our fingertips. The periodic table is a fabulous tool. So then we have this next thing we want to remind you, that when an atom becomes an ion, it's the electrons that change. The number of protons don't change. So once this element has become an ion, either a cation or an anion, we are still going to see that column for the number of protons stay exactly the same. They do not change. We want to always be reminded metals lose electrons to become positive ions, which we call, you should know this, cations. And then, of course, nonmetals gain electrons to become the negative ions, which we call anions, a negative ion. If you're hearing me say this multiple times, you know that that's important to know. And this is certainly not the first time that we've gone over that fact. Backing up, what's going to happen here? We're talking about those metals losing 1, 2, 3 electrons. We're talking about fluorine only needs 1. Only 1 electron needed to get 8. Oxygen needs 2 electrons to have that octet 8. Nitrogen needs 3. So after that change, so here we look at the number of electrons in the ion. We find that helium has 2 electrons, and that's our noble gas. Lithium now is what we call isoelectronic. It's not a word I'm probably ever going to quiz you on. Oh, my L's not coming out there. Isoelectronic. That is meaning that it has the same electron configuration. So once lithium gives away that electron, it has 2 electrons, and it is isoelectronic, or has the same electron configuration as helium. Does it become helium? Of course not. The protons don't change. The protons are different from helium to lithium. But then we know that beryllium has given away 2 electrons. It is also isoelectronic, which means has the same electron configuration, the same number of electrons as helium. And then with boron giving away 3 electrons, now again, same electron configuration as helium. Notice we have this plus or minus 4. In terms of energy, it's going to be the same energy required to collect 4 extra things as to get rid of 4 extra things. That's the idea there. So since that energy change would be similar for those, carbon, it's suggesting here that it can go either way. It can either add or subtract electrons. Later you're going to find out that what carbon tends to do is share electrons, and that's in the next section. That's the next unit that we're going to be talking about. So here we have nitrogen, which has gained 3 electrons, oxygen's gained 2, fluorine's gained 1. All of those now have the same electron configuration as another noble gas, neon, which has 10 electrons. So again, this pattern, it's repetitive, but it's so important that you see the big picture, because what this particular practice sheet was all about wasn't remembering where the atomic number is and to how to tell the number of protons, but to see that this octet rule, when these atoms change number of electrons, they either gain or they lose electrons to become an ion. They are doing that in order to achieve that octet. And of course, why is it that the noble gases don't react? They already have that octet. They don't need more electrons. They aren't giving any away. And that is the answer key to that worksheet.